Hello, everyone. This is Daniel Dibaba. Today we will discuss about the nuts and bolts of linear regression. Can you hear my sound?
Yes, we can hear you.
Thank you. So the objectives of today's presentation is to define linear regression, to describe the assumptions of linear regression, to describe when to use linear regression, and to describe the outputs of linear regression. So linear regression is a statistical method that's used to examine the association between a given predictor variable and a continuous outcome variable. So one of the important requirements for linear regression is that the outcome variable has to be a continuous variable. So linear regression is used to find a solution or a coefficient for a linear equation. Linear regression, we have the formula y equals alpha naught plus beta times the predictor variable x plus residual e. So in this equation, y equals alpha naught plus beta x plus e, the y is the dependent or the outcome variable, and alpha is the y intercept. So if this is an equation for a given association between a given variable x and an outcome variable y, the alpha naught is the intercept. So when x is 0, or when, for example, if we say x is gender, the reference is considered as 0. The reference is considered as 0, and when so if say the reference is female, for male, the y-intercept would be when the intercept would be when the variable for x or gender, when the gender is female. So if we take other examples, for example, a binary categorical variables, which has 2 levels, the intercept is the value of y when the level is the reference level. So that means, for example, if we say the reference for gender is say female, and then the y when the reference is when the x variable is female gives us the intercept variable, and we'll see this when we look at the output of linear regression. So it's, and the beta is the coefficient of x or the solution, and e is the residual. We'll see what the residual is. The residual is, so based on the beta coefficient that we obtain and the intercept, we estimate the y values or the continuous outcome variable. And this most of the time deviate from the real observed data. So this deviation from the real observed data is what we call the residual or error. So to select the correct data analysis method, we usually rely on several informations, such as required assumptions. And most models or regression models have their own assumptions. And the data has to meet these required assumptions for us to be able to use the given regression method. The distribution of so the distribution of the outcome variable is the other required requirements that helps us to determine which statistical analysis method to use. So for example, in case we have a continuous outcome, we look at whether the continuous outcome is normally distributed or not. When we say normally distributed, that variable has certain way. When we graph it, it should have a bell-shaped curve with a mean at the middle, and usually also the median around the same, and then a flat tails. So when the data has that kind of bell-shaped curve, we say the data is normally distributed. We also use quantile plot. We'll look at that later on to check whether a given data is normally distributed or not. So the distribution of the outcome variable is one of the criteria that helps us to determine which statistical analysis method to use to analyze the association between given variables. If the data is non-normally distributed, we might have to use a different technique, or we have to transform the data to normality using like log transformation or other methods. If the data, the outcome variable is binomial, that means it is categorized. For example, an event happened or not instead of a continuous form. We will use a different statistical analysis method than linear regression. So to select the correct statistical analysis methods, we need requires meeting the assumptions and the distribution of the outcome variable, the research question or hypothesis. The research question might be, you might be interested in predicting the outcome variable, or you might just want to see if there is a difference between certain groups. So based on your research hypothesis, you select the given statistical analysis methods. The other information that we use to determine what data analysis method to use is the assumes relationship between the variables. Is there a linear relationship between the variables, non-linear relationship between the variables, a logistic form of relationship, especially when the outcome variable is a binomial or a given event, a yes or no type of outcome. And the purpose of the analysis is that testing associations. Are we interested in prediction or predicting what would be the given the blood pressure of a given patient if the height of the patient is this much? So that is prediction. And testing association is whether to examine whether there is a relationship between two or more variables. And dimension reduction is another data analysis. Data analysis aims or goals. So to select a given data analysis method, we rely on this information and extras. So we rely on data assumption, required assumption for a given analysis method, the distribution of the outcome variable, the research question or hypothesis, and the assumed relationship between the variables and the purpose of the analysis. The linear regression has certain assumptions that the outcome variable has to meet for us to use the linear regression method. So these assumptions are linear relationship between the predictive variables or X variables and the outcome or Y variables. There has to be a linear relationship. When we say linear relationship, as one increases, the other also increases, or as one increases, the other decreases. This is a linear kind of association. And the second assumption for linear regression is IID, or independently and identically distributed residuals. So residuals are, we say, they are errors. When we predict the given outcome variable, usually the observed and the predicted would be slightly different. Those difference or the deviation from the observed and the predicted one are called residuals or errors. And these are so related to the outcome variable. And so in the IID, the independently distributed mean the measurements on subjects are independent. There is no relationship between subjects. So for example, if our observations are family members, there is likely to be association between observations. If the observations are repeated on the same participant, again, the observations are not independent. For us to use the linear regression analysis, the observations on the subject have to be independent. That means if the data are repeated measurements, we can't use linear regression. We have to use other methods. And the residuals are normally distributed. We will look at what normally distributed residuals look like. And the third assumption is homoscedasticity or constancy of the variance of the residuals across the range of levels of the predictors. So the residuals have variance or variability around them. And these variance, if we divide them by the levels of the predictor variables, so for example, the predictor variables can be gender, like we said, a female and a male, and the outcome variable that we are interested might be the blood pressure or systolic blood pressure. So if we predict systolic blood pressure by gender and look at the variance of the residuals based on male and female, and in both cases, the variance should be constant. In male and female, the variance of the residuals systolic blood pressure should be constant. And this is called homoscedasticity. There are ways we can investigate or examine whether the assumptions of the linear regression are holds or not. So we rely on model diagnostics, model assumption diagnostics to make sure that our data meets the assumptions of linear regression for us to be able to use linear regression for the analysis. So one of these is plotting the residual versus the dependent variable. The error, so again, I want you to understand that the residual stands for the error between predicted a Y value or dependent variable value, in our example, the systolic blood pressure, and the observed. So for example, if we sample 10 people or 10 patients that show up at the emergency department or outpatient department and measure their blood pressure and look at the association between gender and blood pressure. And so when we run a linear regression, it gives us a coefficient, it gives us the intercept, and it gives us also the residuals or errors. So there are always errors around the model. And so based on the coefficient and the gender of a given patient, we can predict what the systolic blood pressure can be. And this again has a residual or error. And if the error versus the plot of residual versus the dependent variable does not follow certain pattern, we say the linearity assumption holds. We will see this in plots. So plot the residual versus the dependent variable, plot the fitted or predicted versus the residuals. This is used to check independence. And quantile plot, this is used to check normality. We'll again look at what quantile means, arranging the data into percentiles or quantiles and comparing this to an empirical quantile that is drawn from a normally distributed data. If the data points fall on a straight line, we say our data is normally distributed and that meets the assumptions of linear regression. And so we will be able to use linear regression for the analysis of the data. The scale location plot is another plot that we use to check constancy of the variance of residual or homoscedasticity. Another one is plotting leverage versus residuals or plotting the Cook's distance versus observations. The last one is to check for influential outliers. So these four figures are figures that usually we can output from the model that is used for linear regression analysis or linear regression analysis outcome. The first one is the plot of predicted values. Like I said, systolic blood pressure against the residuals. The residuals are on the y-axis. They are the errors around the fitted or predicted values. And we have the predicted values on the x-axis. So we have scatter plots, and if the red line lies along the horizontal line, which is 0, we say there is a linear association between the given x variable and the y variable. And we can use a linear regression analysis to conduct a analysis for this kind of data. If the the red line deviates a lot from the line which lies horizontally on 0 residual, and then or if there is curvature in the red line, this tells us that the assumption of linearity is violated. Again, if there is curvature, the assumptions of independence and independent observations is violated. So the plot of predicted values or fitted values versus the residuals help us to examine whether the linearity assumption is met, whether the independent assumption is met. And the second one on the right here is normal quantile plots. So on the x-axis, we have theoretical quantiles that are drawn from normal distributions. And on the y-axis, we have studentized residuals. And these are residuals divided by the standard deviation of the residuals. And so if the data point is, the scatter plot of the data point is from our sample lies along this diagonal line, we say the data is normally distributed. We will see other examples where it deviates from a normal.
This whisker tastes really bad.
Plot. So for example, if data points are found somewhere here, and here, if this is not a straight line, and then we can use the linear regression for the analysis of the association between our given predicted variable and the outcome variable. The third one is the scale location. This is similar to the first one. It is used to check homoscedasticity or constancy of the residual variances. So again, if there is curvature in the red line, or if the data is distributed in a way that has a given pattern that deviates from a random distribution like here, we cannot use the linear regression for the analysis because the data violates the assumption of linear regression. The last one is residual versus leverage plots. So in this case, we have studentized residuals on the y-axis and leverage on the x-axis. So the leverage, as we will see in the next slide, is tells us how far a predictor variable for a given observation is away from the other observations. So for example, when we have a given x variable which predicts our y variable, a given individual among our sample might have a very outlying value. And the leverage is a measurement of how far such an observation is from the average of all the other observations. And so on the x-axis, we have the leverage. On the y-axis, we have studentized residuals. And we also have Cook's distance on this figure. If there is an outlier, the Cook's distance appears at the right-hand corners and left-hand corners at the corners. And any observation that falls beyond that red line of the Cook's distance is taken as extreme or an outlier. So let's look at each of the assumptions for linear regression one by one. Let's look at the linear regression, linearity assumption. So the one of the assumptions in linear regression is that there is linear association between the x or predictor variable and the outcome variable. If the linear model does not reflect the actual association between your variables, the parameter or beta coefficient estimate the confidence intervals that you can create around the beta coefficient, and the p-values might be meaningless. If the linear association does not describe the relationship between your x or predictor variables and outcome variables, you might still be able to estimate the coefficients, but they are meaningless. If the association between the predictor variable or x's and the dependent variable y is linear, the residual versus the dependent plot would overlap the line of best fit. Also, we'll see in the next slide. And if the horizontal line on the residual versus fitted values or predicted values plot is straight, the association is linear. So this is the plot of the fitted versus residuals or residual versus fitted. So the horizontal line in this figure is almost straight, and the scatter plot of the residual versus the fitted values do not follow a given pattern like curvature. So the linearity assumption generally holds in this case. So for example, if the red line is instead some way like curved one, bell-shaped or something, it indicates that the association between the x and the y variable is actually not linear one. It might be a linear association. So the linear regression is not appropriate for that kind of data. And again, we are looking at linearity. This is a plot of the x or predictor variables against the y variable. component or predicted residuals on the y-axis and the x variable on the x-axis. If the blue line falls on the red line, the line of best fit, then the association is taken as linear. And the association between x and y is linear in the first figure for the x, but for that of cylinder, in the second figure, there is deviation from the line of best fit. So for the cylinder, again, as the MPG, miles per gallon, we have the red line slightly deviating from the blue, the blue line deviates from the red line. So this is an indication that linear regression might not be appropriate for examining the association between the cylinder and miles per gallon. Sometimes we would look at these kind of figures and say the deviation is not too much. We can still use linear regression for this analysis. Other times, if the deviation is too much and very marked, and then we decide to use other methods for the analysis, or we might transform one of the variables to make sure that the association is actually linear. In the third figure, again, it deviates from linear association, weight versus miles per gallon, weight of a car in tons and miles per gallon. The association does not look like to be linear, but the deviation is again not too much. Independence. So as I said in the previous slides, to examine whether the observations are independent, we fit again the fitted values or predicted values again in the residuals, or the residuals again as the fitted values. If the line, the red line is horizontal and lies close to the zero residual, we say there is no risk of associated related observations. So we can assume that the observations are independent and we can use linear regression for the analysis. We can also examine autocorrelation between the residuals using Darby-Watson test. It gives us Darby-Watson estimate in the statistic and p-values. And if the p-values is statistically significant, we say there is autocorrelation between the residuals, and that tells us that the assumptions of independence among the observation is violated, and we cannot use linear regression for that kind of analysis. In our case, looking at the association between x variable and y variable, the p-value is 0.94, which is greater than 0.05. And so there is no autocorrelation between the residuals. So the independence assumptions of the residual hold this, and we can use the linear regression analysis. Normality again, this is a bigger figure. We have the theoretical quintiles drawn from normally distributed variables on the x-axis and the quantile from our observed data on the y-axis. And when we plot against each other, if the data point is from our observation lies straight on the y equals x line like here, and so the data points lie straight on the straight line, we say the data is normally distributed. So we plot again the residuals And if the data points do not deviate from the straight line as in this figure, we can use the normal, we can use the linear regression for the analysis. The normality assumptions of linear regression hold this, and so we can use linear regression analysis without violating the assumptions of linear regression. So when the data points lie on the straight line, the residuals are normally distributed, and that means the outcome variable is normally distributed. If the data deviates markedly from the straight line, then the normality assumption is violated. So for example, if our data outcome variable data is a rank variable or a scale variable, instead of having this beautiful straight line, we have chopped horizontal line based on the different levels of the given outcome variable. So for example, if we say the outcome variable has ranges between 0 and 10, like a pain score, those data would be very straight horizontal lines at each data point. So for example, around here somewhere, or they deviate from this straight line. That tells us that we cannot use a linear regression analysis to examine the association between this outcome and a given predictor variable. We can also test normality of the residuals using Anderson-Darling normality test. Again, in this case, it gives us a p-value above 0.05, which tells us that the data does not deviate from normal distribution. The homoscedasticity or constancy of variance. So this figure is the fitted versus the square root of the student times residual. Again, this red line should be a straight line. In this case, it slightly deviates from a straight line. When it slightly deviates from the straight line, usually you sit down and look at the figure and say, should I continue to use the linear regression analysis, or should I transform the variable to meet the assumptions of linear regression? In this case, if the plot of the fitted values versus the square root of the standardized residuals shows a random distribution around a straight line, and you have a beautiful horizontal red line, the assumption of constant variance holds. In our case, this assumption is, like I said, is questionable because we have a curvature at this point. And a formal test also indicates that the variance is not constant. So we can test whether the variance of the residuals is normally distributed, and the p-value here is less than the 0.05 mark of significance, which tells us that the homoscedasticity or constancy of variance for the association between x and y variable does not hold, and using linear regression is slightly questionable. So the last assumption for the linear regression is looking at outliers, extreme observations, influential observations. So outliers are data points with an extreme values of the response variable y, or the outcome variable, the predictor variable, or x variable, or both variable. A given for a given observation might have both can be outlier in terms of the x or the predictor variable and the outcome variable. A given observation might have a very extreme values for the y variable, but normal range of the x or predictor variables, or both variables can be extreme. So when we have outliers or extreme observations in our data, we have to look at them and make sure these observations are actually valid. Sometimes when we enter the data, when the data are collected, there might be an error in data entering, and this can result in outlier. For example, for blood pressure, systolic blood pressure, if a given patient blood pressure reads 200, and then we have to make sure that number is actually right. 200 systolic blood millimeter of mercury. We have to make sure the data is entered correctly. If the data is entered correctly, but it deviates from the other observations, we have to examine, are we interested in this observation? Should we keep the observation in our analysis and make such kind of decisions? So there are different ways of examining whether we have outlier in our data in linear regressions. Leverage data points are one way of examining the extreme or influential variables. So the leverage data points are the data points with an extreme values in the predictor or X variable. And leverage ranges between 0 and 1. Another one is the Cook's distance. Cook's distance is the measure of the changes in regression coefficients when an observation is omitted. Actually, so the Cook's distance is the change in the predicted value of the Y or the outcome variable when the given observation is omitted. If the deviation is too much, when we omit, for example, the first observation and predict the Y variable for the Y variable, if the deviation between the observed Y variable and the predicted Y variable is huge, and then we say this variable or this observation, the deleted or dropped observation is influential. The Cook's distance identifies influential data points, and the cutoff points for the Cook's distance is it varies based on individuals. Some take the cutoff point of 1, others use 4 divided by the sample size minus the number of parameters that are estimated. So for example, if we are looking at 2 continuous variables, like we said, if we look at the association between, say, the height of a given patient and the systolic blood pressure, we are looking at 2 continuous variables. And so we estimate the intercept and the coefficient for the X variable. So we estimate 2 parameters. And in that case, so if we have 100 observations or the sample size of 100, the cutoff point for the Cook distance, according to the second one, would be 4 divided by 100 minus 2, the intercept and the beta coefficient, which gives us 4 divided by 98. So the Cook's distance is given by this formula, which is the sum of J equals to 1 to the sample size, and the predicted Y when the I's observation is dropped, minus the predicted Y when that observation is retained, squared divided by the number of parameters that are estimated, times the variance of the residuals, which is given down here. So this is the figure that we use to examine whether there are influential variables. And the first one is output from the linear regression model. And so, like I said, if we have red lines around here, and there are some data points that lie beyond that red line as the right hand corner, a left hand corner, and or right bottom hand corner. We say those observations are influential. And so if there are influential variables observation in our data, sometimes we look at them. Are they recorded correctly? And are the data valid? Should we omit them from the analysis, or should we keep them? And so we make those kind of decisions and proceed with the data analysis. The estimated coefficient, beta coefficients, and the p-values might be different based on whether we keep these influential variables or not. In the examination of the association between the x variable and the y variable, which are random variables that are generated, the 52nd observation, the 76th observation, and 85th observation seem to have large leverage, which means there is an extreme x values for these observations, the 52nd, 76th, and 85th observation. And again, so the first one is the plot of leverage against the studentized residuals, and also with the Cook's distance of light. The Cook's distance appears based on whether we have an outlying variables. In the second figure, we are plotting the number of observations. So like participant IDs and the Cook's distance on the y-axis. We said if the Cook's distance lies above 1, the cutoff point some use is 1, others use 4 divided by the sample size minus the number of parameters. And the second one is very conservative. It can identify, so it lies around here. When we divide 4 divided by 98, we get about 0.04 something. So all the observations with the Cook's distance above this line are raise concern. There might be outliers. We have to examine them and make sure they are entered correctly in the data. So the Cook's distance plots or residuals versus leverage plot indicates influential observations. And wherever there are extremely influential observations, the Cook's lines appear at top right and bottom corners in the first plot. And the observations that fall beyond those lines are extremely influential. So this is a figure from another output, and this figure, I feed a model on the miles per gallon for cars predicted by the number of cylinders and the weight of the car. And it looks like the assumptions of linear regression are violated. In the first plot, we have a curvature in the fitted or predicted versus residual plots. And we said if the linearity holds, this red line should be straight on the residual equals 0. In this case, it shows some curvature, which means it deviates from the assumptions of linear association. And looking at the quantile plot, again, it's not really the typical straight line that you are looking for, but it's not too much deviated. Usually looking at the quantile plot of this type, you might still decide to retain it. Especially we pay attention to the middle of the figure. If there is too much deviation from the straight line at the middle, we say there is a violation of normality assumption. The third figure is the scale location. So fitted versus the square root of the studentized residual. Again, this shows a curvature, which tells us that the homoscedasticity or constancy of variance for the residuals is violated. In the last figure for influential variables, here we have the Cox distance plot appear at the right top corner, and our right bottom corner and the left corners. If we have some observations that fall beyond those red lines, these lines, we say we have influential variables, and we have to make sure those data points are actually valid data points. So this is the output from linear regression. We have the miles per gallon, and we use a cylinder. Cars having 4 cylinders are the reference values. They are not visible in this table, and so they are omitted. They are the reference. And we have cars with 6 cylinders and 8 cylinders, and we have the intercept, which means the miles per gallon for those with 4 cylinders holding weight constant is around 34, and the 95% confidence interval range is between 30 and 38, and the intercept is statistically significantly different from 0 because the p-values is below 0.05. And for those with 6 cylinder compared to those with 4 cylinders, the beta coefficient is negative 4.26, which means if we instead have 6 cylinders, the miles per gallon will be reduced by 4.26. And this ranges between negative 7.9 and negative 1.42. Again, this is significant, statistically significant at 0.05 p-value. Instead, if we have cars with 8 cylinders, the miles per gallon will be reduced by negative 6. So the number of cylinders is kind of inversely associated with the miles per gallon of a car. And the weight of the car is also inversely associated with miles per gallon. So as the weight of the car in turn increases by 1 unit, the miles per gallon of the car decreases by 3.21. This is again significant, statistically significant at alpha level of 0.05 because the p-value is less than 0.05. So in this table, we have the number of observations, which is 32. And we have the R square and the R adjusted square. So the R squares tells us the percentage of the variability in the outcome variable that can be explained by the predictor variables. So cylinders and weight of the car explain about 84% of the residuals or the variability in miles per gallon. So one can use the coefficient estimated from linear regression to predict a given miles per gallon for a given car. For example, sorry. So the intercept is actually 34. I think I used this one from previous table. So the intercept is 33.99 or 34. So SRT4 minus 4.26 times cylinder 6. If cylinder of the car is 6, it would be 1 here. We put 1 here, and we put 0 here. And again, we hold the weight, and we can estimate the miles per gallon for a given car. Instead of six cylinder, if the car actually has 8 cylinder, we make this 0 and this one 1. So it would be 34 minus 0.426 times 0 minus 6.07 times 0 minus 3.21 times the weight of the car plus the residual. Usually we leave out the residual, so we have a predicted value of the miles per gallon for that given car. This is a different table output or regression table output, but in this case, instead of considering cylinder as a categorical variable, we took them as a continuous variable. So this is when you end up misspecifying the model. If you misspecify the model, considering cylinder as a continuous variable, you get certain beta coefficients, and those beta coefficients are not valid. So you have to make sure that you correctly specify the variables in your models. If there are categorical variables, you have to make sure that you specify them as factors in your models. Otherwise, you will get a beta coefficient that is different from the one when your models are correctly specified. And for example, in this case, the intercept is close to 40. And when the cylinder increases by 1 unit, we have a reduction in the miles per gallon by about 1.5. Say if the cylinder increases by 2, the miles per gallon decreases by about 3 points. So this model is not a correctly specified model, but just for example. For weight, again, it's similar with the above one, negative 3.19. In the previous slide, we have negative 3.21 because in this model, we misspecified the cylinder as a continuous variable, and so we got a different coefficient for the weight as well. And so when one uses linear regression models or other regression models, we have to make sure that we specified the association between the variables correctly. The models should be specified correctly. Otherwise, we get a different or a biased beta coefficients and the p-values. So we said the assumptions of the linear regression is that the outcome variables have to be a continuous variable. The continuous variables are like blood pressure, cholesterol levels, age, the dose of medication that are given to patients. So those are continuous variables. Categorical variables are like gender, race, region, color, and the type of treatment that is provided, whether you treated your patient, inpatient, outpatient, whether you treated the patient with surgery or medication or things like that, categorical variables. So if the outcome variable is a categorical variable, we cannot use a linear regression. If the outcome variable is ordinal scale or a rank kind of variable, like pain scores, like the degree of range of motion of shoulder or joints, those kind of things, or if there is a Likert scale kind of data, we cannot use linear regression because we violate some assumptions of the linear regression. The outcome has to be continuous variable. The association between the X and Y variables have to be linear. The observations have to be independent. The homoscedasticity or constancy of the variance of the residuals, and we have to look at the outliers as well. So for categorical outcome variables, we cannot use linear regression. For ordinal scale outcome, we cannot use linear regression. For non-normally distributed variables, we have to first transform them to normal distribution before we can use linear regression. So linear regression, we need a continuous numeric response or outcome variable, and the residuals or the error terms have to be normally distributed. We use the quantile plot to check whether there is a normal distribution in the residuals. And the subjects or the participants should be independent. If our data contains repeated measurements, we cannot use a linear regression analysis to examine the association between our predictor variables and outcome variables. Instead, there are hierarchical regression analysis and those kind of other way of analyzing the association between repeated measurement outcome variable and predictor variables are analyzed using different methods. So the subjects or the observation should be independent, and the residual variance should be constant across all levels of the predictor variables. And we have to check for influential extreme observations and make sure if there are outliers or extreme observations, we have to make sure that those observations are actually valid. And we have to make a decision whether to retain those in our analysis or drop out from the analysis. So thank you very much for your attendance. I might have some questions. Yeah, so if you have any question, you can raise your hand or you can send me in a chat and I'll be able to answer your questions. So it looks like so far nobody has a question. So we said for determining a given data analysis method, we look at the certain requirements like the assumptions of the models, a distribution of the outcome variable, the hypothesis that you have about the association between the variables that you are studying, and influential variables, and the purpose of your analysis, whether it is to predict the outcome variable or whether it is actually to examine associations, or whether you want to conduct that dimension reduction. And so that's it for today. There is no problem. I felt no problem at all. So Dr. Mark, it's fine with me. Thank you for attending.